Thank you. And, I think it's perfect time for a nap, so I'm very grateful to see you here. And I'd like also to thank the organizer for the invitation. I think it's a very great event, and I was very pleased to be here this week. So my talk will discuss how to perform some global sensitivity analysis in a stochastic system, and perhaps to motivate a little bit this question and the methods I'm going to introduce. I must say that for many years we have been working on uncertainty quantification, but essentially parametric uncertainty, so models having some parameters that are not well known, and we develop techniques to deal with this situation, so parametric uncertainty. But in many situations, the model itself is not deterministic. Okay? So it's not that we have parameters that we don't really know which value to give, but the dynamic, the evolution of the system in time is truly stochastic. So we have some inherent stochasticity. So many physical systems have these situations. It can be because at very small scales, usually you have noise, say typically thermal noise that can appear. And so the evolution is really inherently random. So here I'm thinking of molecular dynamic chemical systems for very small size reactors, for instance. Reactors could be biological cells, if you want. There are also situations where there are some forcing acting on the system we want to simulate, and there's no way we can predict what will be this forcing. So this could be, for instance, the case in finance. It could be the case in many situations. In energy, think, for instance, of a wind turbine. It is submitted to turbulent winds, storms, or whatever, and you cannot predict a priori what condition the machine will have to stand and support. So in engineering, stochastic modeling becomes very important in that case. And there are obviously the situation of all models that in order to maintain tractability, computational tractability, we have to reduce, we have to solve at, say, coarse scales, while we know that at smaller scales, there are some phenomena that we are completely neglecting. Sometimes we can average or by some homogenization techniques upscale these effects, but there are situations where we don't know how to perform such upscaling, and one possibility in this case is to add some random noise that mimics the effect of the small-scale process that we cannot model. That's the case, for instance, in climate modeling, where they had some random noise to force the flow at small scale to mimic the effect of turbulence mixing. Okay, so stochastic modeling, and here I'm just thinking about physical models, but you can think of all models related to social science, for instance. So stochastic modeling is very common. It can be very complex. It's a very nice way to deal with things that we cannot prescribe or that we don't know. But the cost of doing so is that usually you have to prescribe some parameters. Typically, you say, I don't know what will be the wind, so I decide to model it with a stochastic process, but now I have to prescribe some parameters, say time correlations, intensity of the wind gust, or things like that. So we have now systems that have some inherent stochasticity, because this is a modeling choice that we made, and some parameter. And these parameters usually cannot be measured. They need to be learned or to be inferred from information. So if we have some experimental data, for instance, but they are not certain. So now we have two sources of uncertainty. One that is inherent to the model, and the second one that comes from lack of knowledge about the parameter. And this is really the question we wanted to address with my colleague Omar Knyo, to see how we could propagate and perform some sensitivity analysis in such systems. So I will have two parts in this presentation. In the first part, I will focus on the case of stochastic ordinary differential equations, so typically scalar ones, so equations or ordinary differential equations driven by some Wiener noise. And I will show how we can consider this equation plus some parametric uncertainty on how to solve this equation by means of polynomial chaos expansion. And in the second part, I will go to the stochastic simulators. And treating this type of system, I will have to introduce new questions that we believe are quite interesting. Okay, so, oops. Really, I can see that. So I'm considering a very simple SDE. So X is a state. Here everything is scalar, but you can extend everything to a higher dimension, so to the vector case, for instance. So you have the evolution of your solution X. You have a drifter with C that may depend on X. It could also depend on T. And you have diffusion terms here with here the Wiener process, right? So very classical. So what you can do is, for instance, to simulate this equation to generate sample or trajectories of this system by considering, for instance, Euler Kims. The simplest one you can devise. And what you have to do is to draw some IID normal random variables whose variance depends on the time step. And so you can integrate a trajectory and repeat multiple times, drawing independently realization of this increment. And when you have the set of trajectories, you can build some statistic, mean, standard deviation, correlation, whatever is needed. And if you consider, oh, I thought it was a spider. So if you have a functional of your trajectory, could be just the value at a certain time, or could be an exit time, or whatever it is. So I call it G, and now you can estimate the expectation of this quantity of interest X, okay, simply by sample average. So generating M replicas of a trajectory of the system, okay? So the situation I want to tackle now is exactly the same, except that now the drift and the diffusion coefficient may have some unknown parameter. That could represent, I don't know, spatial variability. That could be just, you know, the magnitude of, if here it's just a random variable, it's just the magnitude of the noise that is entering the system. Okay, so I did not queue these random parameters, and I'm assuming that they have a known probability. So how do you know this probability? Well, perhaps they are coming from some Bayesian inference based on some experimental observation, and that would be your posterior of your Bayesian. Okay, and the main assumption I'm doing here is that the knowledge of the parameter doesn't say anything about the forcing process. Basically, the two are independent, which is quite I think natural, and I don't see a situation where this would not be the case. So it's not a strong assumption. However, it is crucial for what I'm going to develop later. Okay, I'm just here making some assumption about square integrability. So the process has to be a second-order process. If I condition on the random walk, so I still have the random parameter here. So this conditional variance is finite, and exactly the same if I condition on a certain value of the parameter, the variance is also finite. Okay, and this equality here are pointwise. Okay, and our goal is now really to say, I want to investigate how the variability in X depends on the different source of variabilities, which are the Wiener process and the parameter, and I want to separate these different effects and being able to draw some conclusion. So the typical approach that people are following consists in conditioning on a certain value of the parameter, then you average with respect to the process, and you do that for some moment of X. So typically, you're trying to look to the dependence of the mean of the solution of your process as a function of the parameter. Okay, so you average with the process and you keep the parameter out. And you can do that for the second moment. So you have now the dependence of the variance with the parameter. Okay? And now you have functions here that only depends on the parameter, and you can apply the classical sensitivity analysis, or I mean the parametric one that I've been developing, and I will give you a flavor of the ideas that are behind. But here is the idea, and one possibility is to go through the functional approximation of these two first moments, but you could go to higher moments on a polynomial basis, for instance. Okay. And once you have this representation, you can sample as much as you want this approximation and study some statistics that can characterize the dependencies. Okay. Now that's a classical approach. So in my view, you are losing some information because the first step you do is always averaging with respect to the Wiener process. Okay. So there is a loss of information, and somehow you're not too penalized because you can do this analysis for higher and higher moments. But how many moments you need, and it becomes very difficult to interpret the outcome of the sensitivity analysis. Imagine that among different parameters, you can say one is very important for the, I don't know, moment of order 5. What does that mean? It's not clear. So what we want to do is slightly different. It's an orthogonal decomposition of the variance. So X has a certain variance, and I want to split this variance into different contributions. Contribution that is due to the inherent noise, so the Wiener process, contribution that is due entirely on the parameter, and the contribution to the variance of the interaction. And the way we do that is by the Sobol-Hoeffding decomposition of X, where the process that I see here as a function of the Wiener and the parameter is decomposed as a mean value, a function that depends only on the Wiener, a function that depends only on the parameter, and a mixed term. Okay? And we ask this decomposition to be, this function is a decomposition to be mutually orthogonal, and this makes the decomposition unique in the case where W and Q are independent. So that's where my assumptions become crucial. Okay, and here you have the definition of this function. So for instance, the function that depends only on the Wiener is the conditional expectation of X given W minus the full expectation of E. Okay, and you have this. So because these functions are orthogonal, you have immediately the decomposition of the variance. You can normalize the partial variance, and you get what we call the sensitivity indices. So they are all between 0 and 1. Their sum here is equal to 1. This one characterizes the impact of the Wiener process on the variance, this one of the parameter, and here the mixed contribution. I will illustrate this idea of characterization on an example later on. So here is the interpretation of this coefficient, and what you can show is that the variance of the mean with respect to W of X for given value of the parameter, so this is really the variance with respect to the parameter of the mean of the solution. This is actually the variance due to W only. To Q only. Okay, so clear interpretation of what we have classically. However, if we average with respect to the parameter the dependence of the variance to the parameter, we see here that we have the sum of two contributions. Okay, so the contribution due to W, to the Wiener process, and also the mixed term. And actually, there is no way that, given this term here, you can split into these two contributions. That's why we believe that the approach we are proposing is richer. Okay, we have finer analysis. In particular, if you discover that, that SW is really large and dominant compared to the other term, there is very few chance that you can learn your parameter by observation. So this is kind of important conclusion that you can draw. So how to compute this coefficient? What we propose to do is then, because we see the process as a function of W on Q, it is to us quite natural to have a series representation. So I'm considering a basis of so a complete orthogonal set of functions psi alpha, which are functional in Q. Actually, I introduce here the measure of the parameter PQ, so they are an orthogonal family. And we are expanding the solution X in this form. So the coefficient in the expansion, the X alpha, are again stochastic processes. Okay, but they don't depend on the parameter. Okay, so I have this expansion. Now I can plug this expansion in my original equation. I will get a residual. If I truncate my expansion, I get a residual. So I'm requiring this residual to be orthogonal to the representation basis, so to every of the psi alpha I have in my expansion. So I'm forming here the Galerkin projection of my problem. And I end up with a system for the mode or the coefficient of the expansion. And you will notice that this equation, so if you gather all the coefficient x beta in a vector, you end up with an equation that has exactly the same structure as previously, except you were a scalar equation, now it's a vector equation. But otherwise, you can still recognize here a drift term, and here a diffusion coefficient term. And what's quite special is that W is still unique. So if you started with W scalar, you still have the same stochastic process that acts on all the modes, force all the modes. Okay. So I'm not going to detail how this Galerkin machinery is implemented or how it is solved, but basically instead of having a single ODE solved by Euler Kims, now you have a system of ODE, coupled system. But it's not very complicated. Now based on the expansion coefficient that I have in the series here, if I take for say convention that the first of this function is a constant. So x0 will be the mean of the solution, well, mean with respect to the parameter. And now I can have the expression of the different function in the Sobolev-Ding expansion and the expression of the different partial variance, which basically, if you want to compute, say, the partial variance due to W only, you have to compute the variance of x0. Okay, so basically, for each trajectory, you average with respect to the parameter, and you look to the variance of the result. But this is made quite easily thanks to the polynomial chaos expansion. Well, maybe I didn't mention, but typical basis we use here are polynomial chaos. So it's polynomial functions. Okay, so let's take a first example. So linear additive system, and I have two uncertain parameters. One is Q1, it appears in the drift term, so it's basically the location of the attracting point. And for the diffusion, I have another parameter Q2 that appears here, and if I make nu equals 0, I have an additive noise problem, and if nu is different than 0, we have a multiplicative noise problem. Okay? So I will start with nu equals 0, and I will consider also that Q1 and Q2 are independent. So in the case where we have an additive model, so nu equal to 0, we can show that you need just a degree 1 polynomial expansion to exactly capture the solution. Okay? And here are trajectory of the mean mode, x0. So it really looks like typical trajectories for the system, OU process. Here is trajectories for the mode that is linear in Q1, so due to the drifter, and you see that there is absolutely no variability, because basically the system has a completely deterministic evolution if you fix Q1 plus some noise that comes and add, but they don't mix. Okay, so if you fix Q1, so here you average, and with respect to W, and well, this is the average with respect to W. That's all you have. And this is the mixed term, the term related to the magnitude of the forcing. So this one obviously has an impact on the solution. Okay, if we have a multiplicative noise term, now it's a bit different because the two parametric sources can interact. So now you have variability on the linear term in Q1, and obviously as before, some stochasticity in the mode related to the linear term in Q2. You can even go to higher order, but very quickly, due to the structure of the system, you see that there is no variability in these modes. So you could even, if you were smart enough to analyze the structure of the Galerkin system, you could drastically reduce the size of the basis. Okay? There's absolutely no need to simulate these trajectories. There is no variability at all. Okay, so these are just densities of the coefficients in my expansions to show that some of them are really Gaussian, as you would expect for Gaussian forcing, but some of them are not Gaussians, because this is due to the interaction between the modes. Here are also some projection of coordinates in planes to show how there exists some strong dependence between the coefficients, so how the Galerkin system is really coupling the dynamic between the different modes. Here's perhaps the simplest plot you could imagine to illustrate the idea. What we have here is a single realization of the Brownian. So we have fixed the noise, and we are varying the parameter. Okay, so you see here different trajectories for different values of the parameter, but you observe that they are very similar. I mean, they are shifted, they can be enlarged, but they are quite self-similar. Okay, and this is really this similarity that allow to have polynomial expansions that converge very quickly, for sure. Here's the opposite. We have fixed the parameter to a certain value, and we are running different winners, and you see that the stochasticity is clearly very, very much different. Okay, but now we can decompose. So here is a set of trajectories, and you can decompose into the function that depends only on the parameter. So essentially we have removed all the noise, and we just have variability with the parameter. We can do the opposite. That is, we look, or we average over the parameter, and we have here variability that is due to W only. And here is a mixed term, just for illustration. Okay, this one is not that much important. And here are not the sensitivity coefficient I have introduced before, but the partial variance directly. So they are not normalized, because the variance varies a long time, so it will be difficult to report everything in terms of normalized. So if you have absolutely no variability or no uncertainty on the parameter, so they have variance that are both zero, then all the variance of the system is due to the noise. Okay, that's clear. Only W as a source of variability. Now, if you have variability also in the drift term, but not in the magnitude of the diffusion, the total variance in red here is essentially due to the variance due to the noise, and you have a contribution of the parameter, but you have no interaction. That's what we have seen before, where the old trajectory was exactly the same. So this is what is happening here. On the contrary, if you have here a perfectly known drift term and some uncertainty on the magnitude of the noise, what you have now is a contribution of the winner, of course, but also of the mixed term. Okay, and now if you have uncertainty in all the parameters, so drift and diffusion, now you have all the contributions that are non-zero. Okay. So with this way, we can really distinguish what is the inherent variability, what is due to the parameter, and have a very fine understanding of what's going on. Okay, here's another more complicated system. It's I have just changed the drift function. So the system has two attracting branches. Okay, and we are starting from a point somewhere in the middle, and depending on the realization of the Brownian, we are led to go to a first attracting branch or to another one. Of course, there is a non-zero but very low probability that when you have selected a branch, you could also branch to the other one, but this is a very rare event. Okay, and for this system, I'm considering some uncertainty which are on the initial location. So clearly, if I'm starting from the very high point, it's very likely that I'd end up on this branch and not on the second one. So I have uncertainty on the starting point, and I have also uncertainty on the magnitude of the stochastic forcing. Okay. So here is just an illustration of what is happening depending on my starting point. So if I start from the left, I always go on the same branch, or essentially always go to the same branch. If I start somewhere on the unstable point, I may select with equal probability one branch or the other, and on the contrary, if I start on the other side, I tend to always end up on the same branch. Okay. Here's the effect of the noise magnitude. So I'm starting always at the same point. If I have a very low stochastic forcing, basically I always go into the same branch. I mean, it's like deterministic attractor, where I stay on the deterministic attractor. And if I increase the noise level, I am able to change this picture. Okay, but of course we would like to do this in a more quantitative way. Okay. Although we understand perfectly what's happening in the system, we want to provide numbers. So as you've seen, even for a given starting point, depending on the Brownian, or for a given Brownian, depending on my starting point or intensity of the noise, I can either finish on a branch or another, meaning that for large time, my solution can be discontinuous. I mean, I have a branching process, I have a bifurcation. Okay. So the polynomial basis I was using before are not going to work, because, or I would need an extremely high polynomial degree to capture the discontinuity. So we have here to use some multi-wavelet basis with some adaptivity in the parameter space. Okay. So this is just to illustrate. Here you have the mesh of the parametric space, and we have here, I think, initial condition and noise magnitude on the other direction. And what is represented here is the size of the elements over which we have a polynomial approximation. Okay, and here is the result. So you have the evolution of the total variance. What you can conclude is that initially it's essentially the variance that is due to the parameter that dominates. Okay. Essentially, it depends where you start before the noise can have time to act. So as time increases, you have more and more contribution of the noise, but it's not very much important. Okay. And later on, there is the mixed contribution that emerge, which in fact represents the case of events where without noise, you would have uncertainty only the blue one. With the noise, this is just fluctuation around the branch, so to say. And here, the fact that the noise can make you switch from branch to another, which also depends on the parameter. Okay, this is exactly the same, but for a higher noise level. And you see that now the magnitude or the different contributions tend to be more balanced as before, because you have more noise in the system. It's quite what you would expect. Okay, as a final note, here it was made with a Galerkin projection. This can be difficult if you have a complicated nonlinear drift function to perform the actual projection of the system. But you can also proceed in a non-intrusive way by selecting some value in the parameter space, computing the trajectories for these specific values, and then construct by, say, regression, for instance, or quadrature, the coefficient of the expansion. Okay. And you can do that, and perhaps this is a possibility to better illustrate the interest of going through this polynomial chaos approximation. You see that in this case, the coefficients here, or to advance or to compute the coefficient for a given realization of the Wiener, you would have to solve NQ trajectories for NQ different values of the parameter. So the complexity here is from one trajectory you go to NQ trajectory, but if your approximation here is sufficiently converged, then you can query your approximation for any value of the parameter, and so you can resample as much as you want. And if most of the variance is carried by the parameter as opposed to the Wiener, this can be extremely effective. But there remains a lot of work to really analyze and come up with algorithms that somehow balance the parametric error, sampling error, and do something very effectively. Okay, yeah, one final comment here. Here I'm working directly on the representation or the analysis of the whole trajectory. And there is a good reason. For instance, you may want to apply this technique for the case of quantities of interest like exit time, but exit time are not smooth functions. Okay? Not even with respect to the parameter. You could imagine for a given realization of the noise trajectory that goes and exit, you change the value of the parameter, you may be missing the exit boundary and continue and exist much later. So there is really an issue with the regularity. So working directly on the expansion of this function, it will be extremely difficult because you cannot construct such approximation for G directly. However, you can use this trick to approximate the trajectory and resample, and by resampling this trajectory, you can very easily generate many samples of the exit time. Okay. Second part I want to discuss is a case of stochastic simulators. So Raul discussed this, and it was a work with actually Alvaro Moraes, who was a former PhD student of Raul. So it's a different class of systems that are governed by a master equation. Well, if your background is chemistry, that's how you know it. So basically what it says, it specifies the advancement in time of the probability of your system to be in some state x at a certain time t, knowing that it was in a state x0 at time t0. And on the right-hand side, you have basically two contributions. The contribution that makes you leaving the state x at time t, okay, and the contribution that makes you going to that state. So you're receiving some probability mass from elsewhere, and you are dumping probability mass by going elsewhere. And so this is really a balance equation. Okay, so in our case, x will be on a lattice. It will represent typically a number of molecules in a certain system, molecule of different species. And this balance equation here has a sum over k reaction channel. So there are k ways for the system to evolve. Okay. So in a chemical system, you have k reaction. Okay. The function aj here are the propensity function that basically fix the time rate at which the reaction j occur. Okay? And they are generally dependent on the state. Okay? And the mu g here are the state change vector. So each time you have a reaction of time j that occur, you have to update the state of your system, and that's the quantity by which the state is changing for a single event. Okay. So it's a Markov process, and it's used in many different applications. What we have to solve this type of equation, well, there are plenty of techniques to solve this equation, but what we consider is the Gillespie algorithm, which is an exact approach for this system. What you do is that you really keep in time, or keep track in time of the evolution of the system by jumping from a reaction to the next. Okay? So if you have k reaction with current propensity function aj, you know that in the next time interval t plus dt, this is the probability of the next reaction to occur. Okay? And it's exponentially distributed. Okay? So the more reaction you have, the more likely it is that it occurs in a small period of time. So the Gillespie algorithm is quite easy to understand. So you start from your initial state, x0. Then you draw the time to the next reaction. Given that you are in a certain state, you can evaluate the rate of reaction here. You decide of the time to the next reaction. So you will advance your system to this time. And you pick at random the reactions that fire first with relative probabilities that are given by the propensity function. So the ones that have large propensity function are more likely to have occurred first than the ones that have a low probability function. Okay, and then you update your system and you continue till you reach your final time. So it's really mimicking all reaction in the system. Okay, so our goal clearly here is to say, what if I have some uncertainty or so some parameter in this propensity function, how can I deal and propagate or perform the same type of analysis that I had before using this type of simulators? Okay. But, well, actually, we had absolutely no clue on how to do that. Okay. So the first question we wanted to address is, say, even for this simple problem, so I can generate multiple trajectories, I can estimate a variance of the population size at some time t, but I'd like to be able to answer and say, if my question is, among this K reaction, which one are responsible for most of the variability? Okay. So I have no parametric variability, but already I'd like to address this question. Which are the reactions that are causing the most of the variance? Okay. And surprisingly, we didn't find any answer to this question, which seems quite important, but no. What people are doing is that generally they look to the average trajectory, and eventually they look to the sensitivity of this average trajectory with respect to the coefficient here, but it's really indirect. So how can we do that? So here's a typical example of a set of trajectory. You have here two reactions. How to distinguish the effect of the two is really unclear. So let me just generalize a little bit more the Sobolev-Ding decomposition. So I have a functional that depends on n independent random functional, and here I'm just writing the orthogonal decomposition that I had before, but it is generalized. Okay, so I have d random input in my functional. Here's just an ensemblist notation for the Sobolev-Ding decomposition. And here it's the definition of the orthogonality, and here is a variance where you sum about all possible, all functions in your decomposition, except for the first one, which is the mean. So how can you define this decomposition? Well, here are the definition of this partial variance. So if you consider a set of, say, direction specified by the vector u, then the variability due to this vector is simply the variance of the expectation of f given this stochastic input, okay, minus the sum of all the variance of the functions that contain this set of indices. Okay, and you have here the other definition. Okay, and from that you can define two important indices, what I call the first order indices, that is the part of the variance that is due to only a certain subset of input, and only this subset. And then I have the total variance, oops, sorry for that, here. So for a subset of variable or input in U is the index of the input that I want to characterize. So the total variance is not only the variance that is due to this input, but also this input and their interaction with any other input. Okay. The nice thing is that in this situation where I have independent input, I have a nice way, a Monte Carlo approach that was proposed by Sobol to estimate this partial variance and then this sensitivity indices, so first order and second order. And the computational effort you have to do is basically compute correlations between your stochastic output when you keep part of your inputs exactly the same. So you generate exactly the same replica for part of the inputs, and you redraw the inputs that you want to analyze. Okay, so basically for each coefficient you want to compute, you have an additional trajectory to solve. So you double on. But the cost is eventually scaling linearly with the number of indices you want to compute. So if you just want to separate, or if you have K channel in your system, you will have to increase as compared to, say, estimate classically by Monte Carlo a moment or an expectation. Say, now you have to estimate n times or as many input, more trajectories. But it's still linear. Okay, but how to apply this to the stochastic simulator? Here in this Gillespie algorithm, it's very unclear what are the stochastic input. And more exactly, when I draw a random number, I can hardly say, okay, this is a number drawn for a certain reaction channel. Actually, if I change the indexation of the channel, I may completely change the dynamic. So how can I decide of things or inputs that are staying the same for some channel and others that are varying for the channel? And this was really a smart idea by Alvaro Moraes, was to say, okay, what if you go to the Kurtz representation, where you represent here the evolution of your system in terms of independent standard Poisson processes? Because now each channel in this representation has its own Poisson processes. So you can repeat them, or you can resample them, and you can decide to keep the same sum of them and recompute others. Okay? And then you will be able to compute some correlations. Okay, and of course, it doesn't mean that by conditioning on a certain realization of a Poisson process for a certain channel, you don't change the reaction time of this channel, because everything is linked. Okay, so here is typically you have to compute some conditional expectation. So you may fix the value of some of the Poisson processes associated to a subset of channels, and you can resample the other one. Okay, and then you can compute the correlation to get the sensitivity indices. Okay, so if you already have this representation, Kurtz representation, you already have all you need to answer the question of what channels are important in terms of variability.
In fact, this decomposition in a sum of Poisson process, variable or processes, it's done under which assumptions on the coefficients A, the AE?
I don't think there is any particular.
But this is, we cannot. We can make it for any
type of system.
For any type of systems.
Yeah.
Okay, without any assumption on the coefficients AE, I mean
no,
those on the intensities of the jumps, in fact.
No, in this problem you don't have any restriction or assumption.
Okay.
It's also known as the time change representation.
Ah, okay, it's TG, so it's a scaled time.
So each TG here, so the Poisson here are normal, but the argument here depends on the whole.
I see, it's linked to the integral of A. Yeah. Okay, thank you.
Okay, so let's see what the conclusion of such an analysis. Okay, so here I'm considering the simplest system, so the death birth process. So I have individuals that are with birth rate B. It's independent of the state because it's spontaneous generation. It's not couples that are making children. No, it's just So you have a birth that occur once in a while at a rate given by B, and then people are also dying, but at a rate D that is linear in the size of the population. So it's D times X. The more individual you have, the more frequent is to observe a death or people dying, right? Okay, so if you apply the Gillespie or the Kurtz algorithm, you can generate trajectories. There is an invariant measure for t going to infinity, which is actually a Poisson distribution that you have on the right. Okay, and now what we would like is to say in this variance that we may have, say, at t equal 8, is it B that is more important? Is it my coefficient D, or is it the birth or the death channel, actually, I should say? Okay. Do you have ideas? I had none, actually. Okay, so here is the results. So at very early time, all the variability is due to the birth process, because we start with a zero population. So if there is no individual, nobody is going to die, and there will be no variability on the number of dead people, right? Okay. So initially, it's all the birth process that carry the the variability, and as time is increasing, variability due to the death channel is building up. The thickness of this line here represents the distance between the first order sensitivity indices and the total order sensitivity indices. So the thickness of the line represents the interaction between the two channels. Okay? And actually, if you run the computation over a very long period of time, okay, here it's a log scale, you see that eventually the contribution of the death channel is going to die. Okay? Because if you don't have variability in the birth, well, nobody remains. Okay, so over a long time, you need to have variability in the death to have some in the birth to have variability in the death. Okay, and eventually, everything will be due to the birth channel and interaction with death. Okay. Now, a more complicated system. This is a Schlogel system. It's just 4 reactions, well, actually 2 reverse reactions. We have 3 species, B1, S, B2, but B1 and B2 are considered in large excess and are considered constant. So we just model the evolution of the number of individual species S, that we call X. Here as the propensity function. So you have 2-body reaction, 3-body reaction, etc. And here are some trajectories. And for this system that represents the infection of a cell by a virus, you have basically 2 asymptotic states. One is the virus has replicated a lot, okay, or the virus is not replicating and remain at a very low level. So infection is low or infection is high. And you have here the density, not the histogram, or exactly at t equal 8 of the solution. Okay? So for this system, when we carry the analysis we had before, so we want to characterize the effect of the 4 channels that we have, this is what we obtain. The variance is essentially due to the first and second reaction, while the second and third are much less important. We see that we have strong interactions. Okay, but the main conclusion is that first and fourth reaction are the dominant one in terms of inducing variability. And how can this be explained? It can be explained by the fact that it's essentially these 2 channels and their variability that plays on the selection of containing a low level of viruses or giving birth to lots of replica. So selecting the upper branch or the lower branch is essentially dictated by channel 1 and 4. Okay? While the 2 other channels induces some noise, but they are way less likely to induce a complete shift of branch. Okay? And that's what you have here in this plot. So here it's on each of these small plots, you have a draw of N1 and N4, so the Poisson process of channel 1 and channel 4, and we repeat for other realization of channel 2 and 3, and you see that most of the time you stay on the same branch. It's quite unlikely that you shift, while on the other case, which is completely the opposite, you see that you tend to be less selective in your branch. Okay, that's another system, but I have a taxi to take, and I don't think you would be very much interested into the details of these results, but it's just to stress that you can have a quite fine understanding of how the different channels are combining their stochasticity. It's quite obvious that now we are, and perhaps I even have this, you can add some parameters in the propensity function and you consider them as additional independent source of uncertainty. So this is a case, for instance, where you add in the propensity function an uncertain parameter. This is a situation where you draw different Poisson processes. This is a picture you had before, but it's always the same parameter. While here, it's the same Poisson processes, but you change the value of the parameter. Okay? And again, the trajectories are more similar. Okay, and now you are able to separate and say, okay, my sensitivity indices have a contribution due to the parameters, that's the blue one here, due to the channel, stochasticity, and one that is due to the mixture. Okay. And obviously, in that case, it would be quite easy to, I think, to learn the parameter, because our uncertainty on the parameter is the dominant source of variability. So we should be able to learn quite easily these parameters. Okay. And the opposite, if we had here a yellow contribution that would be far up, well, I would say that you don't really care about the actual value of the parameter because it doesn't give you much variance. And it will be very difficult to learn them. Okay, I think maybe I would prefer to answer questions rather than commenting these slides.
Any question?
Like in the first, when you are discussing the sensitivity analysis for the stochastic ordinary differential equation, Thank you. Like when you are discussing the sensitivity analysis for the stochastic ordinary differential equation, you have like capital Q1 and capital Q2, and you assume that they are independent. And you've done the sensitivity analysis in that way. If you just have an idea, if you don't have this independency between this Q1 and Q2, like how it's changing, it's make easier, I think, no? The sensitivity analysis.
Or to consider them independent.
Huh? If I consider them dependent?
Dependent?
Yes. How it change these sensitivity analysis?
Well, first, you could still continue to perform a separation between inherent stochasticity and parametric one, but it would have to be globally, the global contribution of the parameters. Okay. Now, if you want to have a finer analysis and distinguish between the contribution of Q1 and the contribution of Q2, then if they are independent, you can apply the Sobolev decomposition. If they are not independent, you cannot do that anymore. Okay, so there are some, recently there were proposed some techniques to perform this kind of variance decomposition in the case of dependent variable, and perhaps you could reuse them, but the interpretation of the sensitivity coefficient that you get at the end, or the characterization that you get, is not very well understood at the moment. Typically, you have to account between correlation between parameters, and you can have sensitivity coefficients that can even become negative, which is really strange, right?
So thank you, Olivier, for the presentation. So to come back to the sensitivity analysis, so here you have presented something related to pathwise sensitivity, where you condition one motion and so on. But you could also perform a sensitivity analysis regarding the PDE underlying the stochastic differential equation. So that is, we know that the distributions of a linear PDE. Okay, and so you could perform also the PCE on this PDE. So could you comment a bit about the choice of doing one way compared to the other? So what is your motivation?
There are some, well, first I wanted to work piecewise, which was a good motivation. One issue with trying to work directly on the densities or on the master equation is dimensionality. First, I mean, systems that we want eventually to solve are high dimensional. So solving this master equation in high dimensions is very complicated. That's one point. Second point is that the approximation techniques we are using, so polynomial chaos, honestly, they are not that good at enforcing positivity. So expanding a density can be problematic. Okay, that's another motivation. And basically, for us, it was making more sense to say, okay, these simulators are existing, stochastic simulators or your favorite tools. Let's try to reuse this machinery as much as possible. And as you've seen, this is actually what we are doing, not with the Galerking, but okay, Galerking projection is my data, but you could do it non-intrusively, and then you just need to have a solver, which I think is a very strong point for users. I'm not very much aware of people working on a direct solution of the master equation. But yeah, honestly, positivity is a big issue.
Okay, so I think it's time for you to leave, so
Thank you.
let's thank you again.
Thank you very much.